everybody. So today we're going to be solving exponential equations. So for today's lesson, you will definitely want to have the chart that we've been working with handy. So if you don't have this on you, it is posted in Friday's classwork post. So our goal for today is to look at an equation, and we want to be able to solve for whatever the variable is in our equation. If you'll notice in our examples below, our variables actually happen to be in an exponent. So we're going to be using our first property, and this is the property of equality for exponential equations that basically says that if I have a base and it is a positive number other than 1, then on the left-hand side, if I have base b raised to some exponent, if the base is exactly the same on the right-hand side raised to the exponent or some exponent, that's telling us that in this case, x must have to equal y. In other words, if the two bases on either side of the equation are the same, then the exponents must be equal. So I've got a couple of when do I use this, because we're going to be looking at a lot of different types of solving over the next couple weeks. We want to use this property of equality when we have no logarithms in our equation, when the bases are the same on either side of the equal sign, like example A, or we're able to make the bases the same, which we'll look at on the back. So example 1, these are pretty basic type examples. This is saying that I want to solve this equation when 3 to the x is equal to 3 to the 4th. Well, in order for this to be a true statement, I'm recognizing that the base on the left-hand side is 3. The base on the right-hand side is 3. So this exponent must be equal to this exponent. So that tells me that x must be 4, because 3 to the 4th power has to equal 3 to the 4th power in order for it to be a true statement. So that one's pretty easy. Not much work we need to do with that one. But if we look at example B, we still have the same base on the left-hand side as we do on the right-hand side. They're both 7s. But on the left-hand side, my 7 is raised to y minus 7. And on the right-hand side, my 7 is raised to the 11y plus 2. It's not as easy to identify the value that would make the statement true. But as long as this base is exactly the same as this base, then our exponent of y minus 7 must be equal to our other exponent of 11y plus 2. And when we set these equal, we're not worrying about what the bases are. We actually don't even care that those bases are 7. We just want to know this exponent has to be equal to this exponent. And then we're going to go back and check our answer. So I'm going to go ahead and solve this for my y. And I get a y value of -9/10. So then I'm saying, okay, well, is this correct? Is this a true statement? Well, when I solve exponential equations, I always like to go back and check my answer by plugging it in to the left-hand side and the right-hand side, just to make sure that both sides are equal. And I'm going to use my calculator to help me here. So I'm going to do a little check step. So on the left-hand side, I'm going to check to see, does 7 raised to the -9/10 minus 7, because I'm just going back and I'm replacing this -9/10 with the y value, is that equal to, when I take the 7 on the right-hand side and raise it to the 11 times -9/10 plus 2. So I'm going to use my calculator here to help me. So I'm just going to type in this on the left-hand side. So 7 raised to the, I'm going to put that in parentheses, -9/10 minus 7. Doesn't work out to be a very nice number. That's okay. I just want to make sure that it's the same as when I plug this stuff in on the right-hand side. So 7 raised to the 11 times -9/10 plus 2. And that's telling me that this left-hand side decimal is equal to the right-hand side decimal. So that does end up working as my value. So y does equal -9/10. And the last example is a little bit different just because our base is now not a number, like a numerical number that we're used to seeing. E is still a number. But now I have e to the 3x equal to e to the 2x plus 1. Again, it doesn't matter what our base is as long as our base on the left-hand side is the same as the base on the right-hand side, which it is. The bases are both e. So our property of equality, again, just tells us to take our exponents of 3x and 2x plus 1 and set them equal. So if I solve here for x, this is going to give me x is equal to 1. And again, with these values, I like to go back and check them. And this one, we actually won't need a calculator, and you'll see why. The check is pretty straightforward on this one. If I take this 1 and I substitute it back in for this x over on the left-hand side, that's going to give me e to the 3 times 1. On the right-hand side, if I substitute this 1 in for this x, that's going to give me e to the 2 times 1 plus 1. Well, the left-hand exponent is going to simplify to 3. And this right-hand exponent, 2 times 1 plus 1, is also 3. So this is showing me that e to the third is equal to e to the third. So x is equal to 1 must be my value. Okay, so I'm going to have you guys pause the video, and I'm going to have you do the U-try problems. Okay, so if you got the values of x is equal to 7/9 for the first problem, x is equal to 2 for the second problem, and x is equal to -3 for the third problem, you are good to go. So our next example has to do with, well, what happens when the bases on both sides of the equal sign aren't the same? So if we look on the left-hand side of example A, I've got a base of 2, but if I look on the right-hand side of example A, I've got a base of 32. So we're not able to directly use the property of equality here because the base on the left is not the same as the base on the right. So what we need to do in this case is we either need to write one side of the equation as the same base as the other, or sometimes we might need to rewrite both sides of the equation to get the same base on either side. So we're going to rewrite either one side or both sides of the equation with the same base. And the goal here is when we're rewriting to the same base, we want our base to be an integer, meaning we do not want our bases to be fractions. And we want our base to be well, as small as we can go, but sometimes there are going to be other options that we can do. But I think a good rule of thumb is to use the smallest integer base that you can get. And we'll talk about what that means. And this is where your exponent chart is going to help a lot here. So what I want to do is I want to look at example A, and I want to solve this equation. 2 raised to the 4x is equal to 32 to the x minus 1. I usually start with the smaller base. And I say, okay, my smaller base here is 2. Is there a way that I can rewrite 32 as 2 raised to some exponent? So if we look down our chart here, I see that 2 to the 5th is equal to 32. So what I'm going to do on the right-hand side is I'm going to replace this 32 with a 2 to the 5th power. So I'm not going to touch the left-hand side because this already has a base of 2. But I'm going to replace this 32 with 2 to the 5th. And I'm going to rewrite it in a set of parentheses because if you'll notice that the exponent on the 32 is a binomial, there's going to be something that needs to happen here. So I'm going to remind myself that when I put that in parentheses, I'm going to have to do some other algebraic step here with this x minus 1. So when we do have something like a binomial in a exponent, what's going to end up happening is the exponent that you just rewrote is actually going to get distributed to both of the terms in that x minus 1. So again, I'm just carrying down this 2 to the 4x. And on the right-hand side, the exponent on the base of 2 is now going to become 5 times x, and then 5 times negative 1, so minus 5. And now this is an equation like what we had on the first side. The base is 2 on the left-hand side, the base is 2 on the right-hand side. So my exponent of 4x on the left-hand side must be equal to my exponent of 5x minus 5 on the right-hand side. So if I go ahead and solve this for x, this looks like I'm going to get an x value of positive 5. And again, I am going to go back and just double check to make sure that I've done my math correctly, because if x is equal to 5 is the correct solution, then when I substitute it back in on the left-hand side and right-hand side over here, it's going to give me a true statement. So let's check it. So on the left-hand side, in my original, I have 2 to the 4 times x, so 2 to the 4 times 5. And then on the right-hand side, I have 32 raised to the x minus 1, so 32 raised to the 5 minus 1. So this is going to simplify to 2 to the 20th power, and then is equal to 32 to the 4th power. And again, I'm just going to use my calculator to help me here to determine, is this left-hand side equal to the right-hand side? So 2 to the 20 is a very large number. Looks like that's 1,048,576. And I'm just making sure when I do 32 to the 4th, I get the same thing, which I do. Okay, so let's talk about something like example B. And you'll notice that example B and example C are kind of similar. Now we have a fraction on one side of the equal sign. And again, I want to think about getting the same base on either side. So it looks like here my smaller number or my smaller base is going to be a 4. And I want to think about ways to rewrite 1 over 16 with a base of 4. So if I look in my exponent chart, well, I see that 4 squared is equal to 16. Well, that would mean that 4 to the negative 2 power would have to be 1 over 16. So again, I'm going to leave my base of 4 to the 2x plus 6 alone on the left-hand side, and I'm going to take this right-hand side and I'm going to rewrite it as 4 to the negative 1 power. I'm sorry, 4 to the negative 2 power. And in this case, I don't need to worry about parentheses when I rewrite, because on this one, I had something that was already in the exponent on the right-hand side. This one doesn't have anything with an exponent, so I don't have to really worry about parentheses here. But then, now that I see that my base is the same with a 4 on the left-hand side and a 4 on the right-hand side, I'm going to go ahead and set those exponents equal. So it looks like I'm going to get 2x is equal to negative 8, divide by 2. My x value is a negative 4. And again, I can go back and check this in my original. So 4 to the 2 times negative 4 plus 6. I want to check to make sure that's equal to 1 over 16. Well, 2 times negative 4 is negative 8 plus 6. And when I add those together, that gives me 4 to the negative 2 power. And I know that just by knowing my exponent rules, 4 to the negative 2 power is 1 over 16. So x is equal to negative 4 does work as a solution. So if you look at example C, it kind of has some similarities to example B, except now if we look at what the smaller number is, the smaller number is actually this 3 between a base of 81 and a base of 1 over 3. The number that we're really worried about is 3 here. So then I'm thinking, okay, well, maybe I might actually have to rewrite both sides of this equation because I need to get an integer base. I don't want a fraction base. So I'm going to have to rewrite this right-hand side and this left-hand side. And I'm thinking maybe base 3 will work here. So if I look at my column of 3's, well, I see 3 to the first is equal to 3. So that would mean that 3 to the negative first would equal 1/3. And I also have a value here with a base of 3 that will give me an 81. So it looks like on the left-hand side, I can use 3 to the 4th to replace this 81. And on the right-hand side, I can use 3 to the negative first to replace the 1/3. And since both of these already have exponents on them, when I do substitute in, I am going to make sure that I'm using parentheses. So on the left-hand side, I'm going to substitute in 3 to the 4th in parentheses, and then I'm going to raise that to the 3 minus x. And then on the right-hand side, I'm going to replace this 1/3 with 3 to the negative 1 power, raised to the 5x minus 6. And then what's going to end up having to happen here is something pretty similar to what we did in example A. I am going to actually have to distribute out both on the left-hand side and the right-hand side. So on the left-hand side, this is going to be 12 minus 4x when I distribute out the 4 to both terms. On the right-hand side, this is going to be 3 to the negative 5x plus 6 when I distribute out the negative 1 to both terms. And then now that my base is 3 here, my base is 3 here, I can go ahead and set my exponents equal. And then I can just go ahead and solve for x here. So it looks like I get an x value of negative 6, and then I am going to go ahead and check that. And I just have to be a little bit careful with the check here, because when I substitute it back in on the left-hand side, I'm going to have to be careful about that negative, because this is really 81 to the 3 minus the x value of negative 6. So 3 minus negative 6. And then on the right-hand side, this is going to be 1/3 raised to the 5 times negative 6 minus 6. So this is really 81 to the 3 plus 6, so that's going to be 81 to the 9th. And then 5 times negative 6 is negative 30, and then negative 30 minus 6 is negative 36. And again, it doesn't really look like these are equal, so I'm going to go ahead and use my calculator. So I'll do this 81 to the 9th first. That's going to give me a really large number. This is actually written in scientific notation. And then I'm going to check this 1/3 raised to the negative 36. And it looks like the left-hand decimal is exactly the same thing as the right-hand decimal. So that does show that x is equal to -6 here. Okay, a couple more. This one's a little bit different because now if you notice in our exponents, we have a x squared, but our process is still going to start the same. I want to look at my bases. So I have a base of 10 over here, and I have a base of 1,000 over here. So that's my smaller number here. So I definitely probably want to use some sort of base 10 to rewrite. So I don't have to do anything with the left-hand side because my base is already 10. But 1,000 I can rewrite as 10 to the third. So I'm going to go ahead and I'm going to replace that 1,000 with 10 to the third. And because I already have an exponent there, again, I'm going to put it in a set of parentheses. And then I am going to have to distribute out over here on the right-hand side. So 10 to the x squared minus 1 is equal to 10 to the 3x minus 3. And then my base is 10, my base is 10. Go ahead and bring down my exponents and set them equal. And the difference between this one and the other equations that we were solving is now we have a quadratic that's forming, and I know it's a quadratic because there's an x squared over here. So what I'm going to do is I'm going to bring both of these terms on the right-hand side over to the x squared side to get one side equal to 0. So if I subtract 3x, that gives me x squared minus 3x. And then if I add 3 plus -1 is going to give me a positive 2. And then I have my equals to 0 over on the right-hand side. And then over here, I can go ahead and factor this because I do have factors of positive 2 that add to -3. That's going to give me an x minus 2 and an x minus 1 as my factors. And then when I use my zero product property, x minus 2 is equal to 0 or x minus 1 is equal to 0. This is going to give me x is equal to 2 or x is equal to 1. And in this case, I actually want to check both of these to make sure that they work. So I'm going to check x is equal to 2 first. So if I substitute in on the left-hand side, 10 raised to the 2 squared is 4 minus 1. On the right-hand side, 1,000 raised to the 2 minus 1. And then if I go ahead and simplify, 4 minus 1 is going to give me a 3. And then that's going to give me a 1,000 to the 2 minus 1 is the first. And I know that that's true because 10 to the third power is equal to 1,000. I have that right in my chart here. So 2 does work. So then I also want to check 1. So I'll go ahead and substitute back in on the left-hand side. So 10 to the 1 squared is 1. 1 minus 1 is 0. Over here on the right-hand side, 1,000 to the 0 minus 1. I'm sorry, 1 minus 1 is going to also be 0. Well, there's this property in exponents that tells me that 10 to the 0 is 1. And it also tells me that 1,000 to the 0 is 1. So 1 is equal to 1. That does work. So we have two solutions here of x is equal to 2 and x is equal to 1. And then the last two, E and F. So E is a little bit different because if you notice, again, we don't have the same base. I've got a base of 64 over here, and I've got a base of 16 here. But if we notice, I don't have anything about bases of 64 or 16. So sometimes you might have to kind of think about, well, are there smaller bases that I can use? So I usually start thinking about this 16. Well, I know that I can raise 4 to the power of 2 to get a 16. Is there something that I can raise 4 to get a 64? And there is. I can raise 4 to the third to get a 64. So I'm thinking, okay, well, 4 will work. I can definitely rewrite a 64 with a base of 4, and I can rewrite a 16 with a base of 4. But if you notice over in the 2 columns, you can also rewrite with a base of 2 because 2 to the 4th is 16. So I could rewrite that side as 2 to the 4th. And I could also rewrite the left-hand side as 2 to the 6, because 2 to the 6 is also 64. So sometimes you might have multiple bases that you can choose from. I'll go with the 4, though, because that one's a little bit larger than the 2. I know that I said use the smallest integer base, but sometimes it doesn't matter here. So I'll use a base of 4. So I'll rewrite this 64 as a 4 to the 3rd. Again, using parentheses because I already have an exponent there of 2x plus 10. And then I'm going to rewrite this 16 as a 4 squared, again, using parentheses because I already have an exponent there of x minus 3. And then I'm going to go ahead and distribute on both sides. So that's going to give me 4 to the 6x plus 30 on the left-hand side. And then on the right-hand side, that's going to give me 4 to the 2x minus 6. And then base of 4, I can go ahead and set these equal. And then I can go ahead and solve this for x. So I'll subtract 2x, that's going to give me 4x plus 30 is equal to negative 6. Subtract 30, 4x is going to be equal to negative 36. Divide by 4, x is going to be negative 9. And again, I always want to go back and check. So 64 to the 2 times negative 9 plus 10 on the left-hand side. 16 to the negative 9 minus 3 on the right-hand side. That's going to be 64 to the, that's negative 18. And negative 18 plus 10 is negative 8. And then on the right-hand side, negative 9 minus 3 is negative 12. And again, these don't look equal, but I am going to use my calculator to help me here. So 64 to the negative 8. It's going to be a pretty small decimal. And then 16 to the negative 12 is also going to be that same decimal. So the left-hand side is equal to the right-hand side. So that tells me that x is equal to negative 9 is my solution. And then the last one's a little bit tricky because you'll notice that we have a base of 6 on the right or on the left-hand side, but on the right-hand side, we just have a 1. But remember, in order to use the property of equality, we want to make sure that the base on the left-hand side is the same as the base on the right-hand side. And it's got to be a base that's bigger than 1. So if we go back to the notes, it says the base b has to be a positive number other than 1. So that means that I want to, for this one, think, okay, well, if I can't use a base of 1, then I need to use my base of 6 somehow. Well, there's this nice property that tells us that anything to the 0 power is 1 that we actually used in that check for step D. So that means that I could actually replace this 1 on the right-hand side with a 6 to the 0 power. Because then I've got a base of 6, and I know that 6 to the 0 is equal to 1. So I'm going to pull down this 6 to the 2m plus 1, and I'm going to rewrite this 1 as a 6 to the 0. And now I've got a base of 6 on the left-hand side, a base of 6 on the right-hand side, and I can go ahead and set my exponents equal. And then I can just go ahead and solve for m here. So subtract 1, that's going to give me 2m is equal to negative 1. Divide by 2, m is going to be equal to negative 1/2. And then I'm going to check that. So if I substitute in on the left-hand side with a negative 1/2, 6 to the 2 times negative 1/2 plus 1. I don't have anything to substitute in on the right-hand side. I'm going to simplify this. 2 times negative 1/2 is negative 1 plus 1. On the left-hand side, this is going to simplify further. Negative 1 plus 1 in the exponent is 0. And I know 6 to the 0 is 1. So that does check. So that m is equal to negative 1/2 is my solution. All right, so now it's going to be your turn to try some problems on the homework. Good luck. Let me know if you have any questions.